Hello and welcome to this presentation of lithium, existence, reactivity, and application. My name is Don Goff, and I'm glad to be here today. At the end of this presentation, you'll be able to identify lithium on the periodic table, explain why lithium abundance is a problem for the Big Bang nucleosynthesis model, identify where lithium is found and how it is extracted, relate physical and chemical properties to lithium's atomic structure, identify major uses of lithium, explain environmental impacts from extracting lithium, understand toxicological effects of lithium compounds, explain the best method for quantitatively analyzing lithium in battery materials, and state potential advantages of lithium-doped coatings for implants. Uses and importance of lithium. Lithium is a very important metal and is becoming increasingly more important in our society due to its use in lithium-ion batteries in electric vehicles. There are many other uses of lithium, however. One is a high-temperature lubricant. Lithium stearate is found in grease. Due to lithium's strong metallic bonds and low density, it's often used as an alloy for low-density alloys. It's used in synthesizing organic compounds. It's used in medicine for mental health, in particular manic depressives, and there's new studies showing that it possibly can be useful in helping dementia, which is a leading cause of death in the elderly of the Western civilization. It's used as an additive to ceramics and glass, and the number one use of lithium right now is lithium-ion batteries, and this has become the topic of a lot of research and also debate politically and globally. Lithium is the third element on the periodic table with an atomic number 3. That means it has 3 protons, and in its atomic form it has 3 electrons. It's the first metal on the periodic table. It is the first of the alkali metals. The alkali metals include lithium, sodium, potassium, rubidium, cesium, and francium. And it ranks 33rd of all elements in abundance in the Earth's crust. Lithium was discovered in 1817 by Johann Arfwedson of Sweden. He was able to isolate lithium as a salt from petalite. Sir Humphrey Davy used electrolysis to isolate other alkali metals such as potassium and sodium. And about a year after Arfwedson's discovery, Sir Humphrey Davy and William Brandt were able to isolate elemental lithium. Lithium comes from the Greek lithos, which means stone. Where did lithium come from? Well, I personally believe that God created all things in their current form. However, according to Big Bang, lithium theoretically originated in the first 20 minutes after Big Bang, when the universe was supposed to be hot and nuclear fusion was running rampant. And so these lighter elements, according to the Big Bang theory, hydrogen, helium, and lithium were set in the first 20 minutes. However, lithium abundance is a big problem for the Big Bang nucleosynthesis model. And the amount of lithium in the universe should be about 3 times higher than it currently is. In addition, research done at Luna determined that lithium-6 was produced well after the Big Bang timeline and cannot be explained by Big Bang nucleosynthesis. Lithium is found in almost all igneous rocks and mineral springs on Earth. Lithium minerals include spodumene, petalite, and others. Elemental lithium is electrolytically produced from lithium carbonate and lithium chloride. Where do we find lithium? Over 50% of lithium reserves worldwide are located in the lithium triangle of Chile, Bolivia, and Argentina. United States has two major deposits of petamite. in Kings Mountain in North Carolina and Thacker Pass in Nevada. The United States and China are also major producers of brine, just as the lithium triangle is, and that's where we produce lithium through a process called evaporation. Global demand for lithium will grow from 180,000 tons in 2015 to over 1.6 million tons by 2030. So how are we going to increase our lithium production? One way to do it is to increase production from seawater and salt lakes. In this experiment done by Hong et al., they used electrolysis of seawater, and by changing the current profiles, by changing the current up and down and trying different profiles, they were able to accumulate more lithium near the electrodes. And they were able to extract 78% pure lithium from the Yellow Sea of China using 60 watt-hours per mole. Physical and chemical properties. To the right you see a picture of lithium. Lithium has a soft, silvery white appearance. It is stored in an oil instead of in water because it reacts with water and air. It is the least dense of all metals. In fact, it's the least dense of all solid elements in normal conditions. It has a body-centered cubic lattice structure, and it has an extremely high melting point for the alkali metals. It is due to the small atomic radius of lithium that it has such a high melting point. It is very reactive due to its low ionization energy. So lithium has one valence electron, and it's relatively easy to remove. And it has the highest oxidation potential of all elements. Lithium does react vigorously with water, but it is not as spectacular as sodium and potassium. And the reason for that is because lithium has a high activation energy due to the strong metallic bonds mentioned earlier. When lithium does react with nonmetals, and it's one of the only metals that reacts with nitrogen, it forms ionic bonds. So how much energy does it take to produce a lithium-ion battery cell? And so a study was needed to determine the energy needed to produce a lithium-ion battery cell. This was a lab-scale model that was done, and the highest energy cost in the process was 1,300 watt-hours for every watt-hour of battery storage, and that was the dry room. And the cost overall is 1,470 watt-hours per watt-hour of lithium-ion battery cell storage. So it takes a lot of watt-hours to produce 1 watt-hour of lithium-ion battery cell storage. So what are the environmental impacts for lithium? As we stated earlier, lithium exists in brines, and brines exist in underground saline lakes or salars. And what we do is we can pump that brine to the surface into shallow evaporation ponds. Here you see a picture of evaporation ponds on the surface. It takes up a lot of land space. It takes about 500,000 gallons of water per ton of extracted lithium. And some regions like Chile in the lithium triangle may only receive 100 to 200 millimeters of rain. So extracting lithium has a major environmental impact, and mining igneous rock, strip mining for lithium, is also damaging to the environment. Doses of lithium carbonate are given in psychiatric medicine close to the maximum level. High doses, up to 6 times that amount, that were tested on rats cause malformation in offspring. Windstar albino rats received 52.5 milligrams per kilogram of body weight per day. They developed fluid around the heart. They had a decrease in their blood pressure, ischemia, and arrhythmia. A concentration of about 20 milligrams per liter can be lethal. What's the best way to analyze lithium? Secondary ion mass spectrometry has been used as a qualitative tool for lithium to determine lithium hotspots in electrodes. Detection of lithium using energy dispersive X-ray spectrometry is not useful due to the low energy, can't penetrate the glass, and even the windowless ones, lithium does not give off enough energy to detect. So a study was done where time-of-flight secondary ion mass spectrometry using a focused ion beam scanning electron microscope was used, and they said that was best for quantification of lithium in battery materials. I found an interesting application of lithium carbonate and lithium phosphate that's potentially being used in medicine. Hydroxyapatite, which I'll refer to as HA, is a bioceramic material for bone grafting and dental surface applications. Biologically derived HA, usually from cattle, is referred to as BHA, and it can be used in place of the synthetically produced HA. When an implant is placed in the body, it takes time to integrate with normal bone, and so we call that osseointegration, and the time it takes for that to happen is called the osseointegration rate. You can't just manufacture an entire bone or large tooth out of HA because bulk amounts of HA are brittle. So due to the brittle nature of bulk HA, titanium implants are often used. Titanium implants can be made by additive manufacturing, often referred to as 3D printing. While titanium is very strong, the problem with titanium is it does not integrate well with bone. And so on the right, we can see that there's a picture of condyle on the end of femur. And we can also see that there is a titanium implant. So HA can be applied to a titanium surface using pulsed laser deposition. BHA doped with lithium carbonate and lithium phosphate is the subject of the study by Duda et al. So on the right, you see a 3D titanium implant. These types of implants, 3D titanium implants, were produced for rabbit femoral condyles. These were doped with 1% lithium compounds, that's lithium carbonate and lithium phosphate, and they were implanted on the right femurs of the rabbit. On the left femurs, only the titanium implant was used. The implants were removed after 4 weeks and 9 weeks and underwent mechanical stress tests. The implants functionalized with lithium compounds, that's lithium carbonate or lithium phosphate, showed significant increases in bone density and strength in all cases. In addition, scanning electron microscopy showed adherence ratios up to 38% higher for both types of lithium functionalized implants over the plain titanium implant. This means that there was accelerated osseointegration. The coatings that were used were fabricated from renewable and natural resources. Rabbit bone is not the same as human, but the study may serve as a pioneering contribution on how medical devices are manufactured. The accelerated osseointegration is very useful for elderly. Healthy people, it takes a long time for implants sometimes to osseointegrate. For elderly, it would be beneficial if there was accelerated osseointegration. And the prolongation of implant life would help younger patients that receive implants, in that they may not outlive their implant or need another implant done down the road. This is the end of my presentation. Thank you for stopping by.